Alrighty. Hi again, this is Alex Flood, instructor at Central California School of Continuing Education, with another one of my review videos. Specifically this time, I'm getting into the information that you'll find on your state board exam, specific to radiation safety. I've split that section up into 4 sections. The first one is radiation physics, and one of the first subjects to talk about here is X-ray production. Specifically what happens at the target in the X-ray tube to produce X-rays. If you don't know what the X-ray target's all about, please refer to my other video about the X-ray tube, and then come on back and watch this one. So this is X-ray production, target interactions, and factors that affect the X-ray beam's spectrum. So, quick preface to this, there are 4 technical requirements which need to be met in order to harness enough energy, specifically kinetic energy, to produce X-rays. So we all know that electrons flow through electric circuits. In the X-ray tube, we do a neat trick with our electrons, which we get them to travel very, very quickly through open space. And eventually we decelerate these electrons. So there's 4 requirements that we need to satisfy, for technical requirements. First one is obvious: a source of free electrons. We refer to this as thermionic emission. This happens at the cathode, the negatively charged end of the X-ray tube, specifically the area right around the cathode filaments, which are made of tungsten wire. And much like an incandescent light bulb, the electrons are so active around the cathode that they can't stay on and around the cathode wire. So they move off into the space around the cathode wire. For that reason, you might hear this referred to as another term, space charge. Thermionic emission and space charge. In any case, we need a cloud, a source of free electrons, in order to have them so that we can speed them up. So that brings me to my next thing. We need a means of accelerating the electrons, and that's done via a high potential difference. This is why on your X-ray tubes you'll set techniques somewhere in the ballpark of between 50,000 volts and 120,000 volts. That high voltage is what's needed to push the electrons across the gap from cathode to anode. Lower voltages would still push electrons across, but it wouldn't give them enough kinetic energy, enough speed energy to actually produce X-rays. We'll learn kind of why in just a little bit here. All right, so now you've got a source of electrons. You've got them flying across a short gap, about a 1-inch gap, at close to 50% the speed of light. Okay. Now that you've got those 2 requirements satisfied, you've got to stop them. Okay. We've taken electrons which have a mass, and we've given them a bunch of kinetic energy. We've given them a bunch of speed. The scientific way to say that is we've given them high velocity. We need to now slow them down. So we need a means of rapid deceleration. That is our tungsten target. That's our anode, our anode disc. Specifically, our anode discs in our X-ray tubes, they rotate. We could still create X-rays without a rotating anode, but that rotating anode has the nice quality where it gives us a larger surface area to heat up, so that we can make X-rays more efficiently. The last requirement, number 4, this one's often overlooked in the textbooks, sort of given as an implied thing, but all of this must be done in a vacuum. So that's often forgotten by X-ray tech students, is that we can do all of these things, but if our X-ray tube was not sealed from the atmosphere in the room, the electrons would just end up bumping into all the other air molecules and nitrogen molecules and oxygen molecules in the room, and it would prevent us from making X-rays. Some electrons will reach the anode, but they'll have given up a bunch of their kinetic energy, and in any case, the number of electrons hitting the anode would be significantly decreased. So our ability to create X-rays basically relies on the fact that we can do all of this inside of a vacuum chamber, and for our X-ray tubes, that's the Pyrex envelope that surrounds all of the electrical devices of the X-ray tube. Some more statements here to get us prepped for this. At least 99% of the target interactions result in the formation of sub-ionizing electromagnetic radiation. What that means is that most of the interactions with electrons and the target, the anode, results in the formation of things that are not X-rays. Most of those interactions result in the formation of infrared and visible wavelengths of electromagnetic radiation. Those are also called sub-ionizing because they don't have enough energy to cause ionization. In any case, less than 1% of the interactions actually create X-rays. So that's one of the most important things I think for students to understand as they're learning this stuff, is that most of the interactions don't actually make X-rays. Most of what's happening in the X-ray tube is just producing heat. And to get an understanding for that, you can walk right up to your X-ray tube after a good day of use, put your hand up to the lead housing and feel how warm that lead housing is. There's a significant amount of heat created inside there. Lastly, the most important concept for this whole rest of the PowerPoint here is that in all physical interactions, the total energy must be conserved. That means from the outset of the interaction through the onset and into the secondary processes, all of the total energy of the interaction must be conserved. We refer to that as the law of conservation of energy. All right, the energy to produce X-rays. X-rays are electromagnetic waves carrying higher energy than visible light. So I like to remind my students that it's all the same thing. It's all electromagnetic radiation. This is the force of the electromagnetic field. The force of the electromagnetic field is carried by photons, which travel as waves, dual propagating waves of energy that radiate away from their source. The electromagnetic field is what exists, and electrons are the particle that interact with that field. And when electrons move, when they vibrate, jiggle, move, whatever wording you want to say, when they move, they disturb the electromagnetic field. So anytime their position changes, the electromagnetic field is disturbed to an extent, and electromagnetic waves are created by that. There's a way to calculate how much kinetic energy any moving object will have. The formula, and it's not important that it is a simple formula, but it's not so important that you can work this formula out, just that you have an idea for what goes into the formula and what the implications are for the creation of X-rays. So the formula is kinetic energy is equal to 1/2 the mass times the velocity squared. M is the mass of an object and V is the velocity. The important takeaway from this is that energy is exponentially proportional to speed, and velocity, speed, has much more impact on energy than mass does. Notice the kinetic energy is taken by the velocity squared, whereas the mass is halved. Mass is a form of energy, but in our case, the movement of that mass, the velocity of that mass, has a greater impact on the total kinetic energy of the object. All right, so interactions in the anode, the target interactions as we call them. There's really two possibilities for our projectile electron to interact with the atom in the anode. Either it interacts with an orbital electron, or it interacts with the nucleus. It's important to remember as we're going forward that electrons are negatively charged, so they'll be attracted to a nucleus and they will be repelled from orbital electrons. The orbital electrons repelled from the projectile electron and vice versa. With the nucleus is always an attractive force for the electrons. So the first target interaction is the most common one. It's referred to as Bremsstrahlung. That's a word in German meaning breaking radiation, as in it is radiation created when an electron slows down. So I said that when an electron's in motion, it has kinetic energy, and we're trying to take some of that kinetic energy and convert it into a different kind of energy. So go back to law of conservation of energy. So the positive attraction of the nucleus pulls the electron toward it as the electron is passing by the nucleus, slowing it down and deflecting it in its direction. After the interaction that the electron has with the nucleus, it's not so important what that electron is doing anymore. It may retain enough energy to go and have another interaction with another atom, and that other interaction can be Brems, or it can be the other one we're about to talk about if it has enough energy. But anyways, we don't care so much about what's happening to the electron after we've slowed it down. We slowed it down, that's the important thing. When an electron slows down, as in loses kinetic energy, the amount of energy lost in kinetic is converted into electromagnetic radiation. If the electron loses enough kinetic energy in this interaction, as in if it passes close enough to the nucleus, or if the electron loses enough of its overall kinetic energy, we can produce an X-ray photon from this. So in this image, we're showing an X-ray photon created, but remember, go back to the preface, more than 99% of the interactions that happen at the target, this is the target we're talking about, don't create X-ray photons. Most of them create infrared and visible light radiation. Bremsstrahlung accounts for the vast majority of X-rays in the beam. Brems is the reason for, is responsible for the heterogeneous or polyenergetic nature of the X-ray beam. This means that our X-ray beam is going to be made up of many varying energy levels, not all one strength. This contributes to differential absorption by the tissues of the body, and this provides for subject contrast in the remnant beam. Without Brems radiation, we would have no subject contrast, and we would have no differential absorption from the body tissues. We wouldn't be able to have diagnostic X-rays as we have them today. We would actually view basically silhouettes. So on the left is showing a silhouette image, which is a result of a monoenergetic beam. And on the right is a traditional, this is an AP elbow view, projection, pardon me. And this is given because we have a polyenergetic X-ray beam where some of it absorbs, some of it passes through. It's made of many energies, allowing it to have this differential absorption into the body tissues, providing subject contrast. Outlined here are the, for example, the fat pads, which are one of these body parts with very, very low density, and this would not be shown against the soft tissue if we did not have this polyenergetic heterogeneous X-ray beam. With Brems, the closer a projectile electron passes to the nucleus, the more it is decelerated, as in the more energy it will lose, the more kinetic energy it will lose. So in this case, there's one electron passing furthest away from the nucleus and one passing closer to the nucleus. With the electron passing furthest from the nucleus, it has the least interaction with the nucleus. I don't mean for us to take this for truth when I say this, but it looks a lot like the way gravity affects objects as they pass around other large celestial objects. For example, Mercury feels a much stronger pull of gravity because it's closer to the sun than Earth does. It works in a similar way, specifically, it works in a similar way. The further away an electron is from the nucleus, the less the nucleus of an atom can pull on that electron, and therefore the less it will take away in kinetic energy. So the photon of electromagnetic radiation that's created in this interaction will have less energy just because that electron's further away. Now, the requirement for this to work for this statement is that the two incoming electrons both have to have the same initial conditions, the same kinetic energy to start with, one being closer, one being further away. The one that's closer is going to lose more kinetic energy and create an X-ray photon, create a photon of electromagnetic radiation that is more energetic than the electron passing furthest away. Okay. So Brems. Statistically, many more X-rays are produced at low energies than at high energies. So the higher the kilovoltage, the fewer X-rays that are produced. No X-rays can be produced above whatever kVp you set. So if it's 80 kVp, no X-rays can be created that are more energetic than that. Think of it like this. If you set a setting of 80 kVp on your console, all of the electrons traveling from cathode to anode must have less than 80 kVp of kinetic energy. They can have up to that, but they will have to have that or less. None of them can have more than that. And that means that at 80 kV, for example, no X-ray photon you can create will have more than 80 kV worth of energy. And in any setting you set, that's true. So whatever your maximum kV is on your console, that's the maximum energy any one X-ray photon could have. Now, most of the X-ray photons will have less than that because most Brems interactions do not take away all kinetic energy from the electron. Most take away some energy and the electron goes on and has another interaction, and some of its kinetic energy is lost again and again and again until it's finally all gone and the electron works its way back into the electric circuit. So it's not as if one electron has one interaction, loses all of its kinetic energy, and makes one X-ray photon with the equivalent of lost kinetic energy. It may have many interactions, but it can only have at maximum whatever is your maximum kVp. So this graph shows a decrease in quantity of X-rays produced as kVp increases. So that's an interesting subject, is that X-ray production decreases as kVp increases. This is the same map, so I'll move back one slide. This map, graph to this graph. Okay, it's the same graph. All they've done here is they've removed all of the low energy X-ray photons because they would otherwise absorb within the patient and just add to patient exposure, and they would not have the potential to transmit through the patient and create add to the diagnostic quality of the X-ray beam. So filtration removes most of the X-rays at low energies from the beam that is ultimately emitted from the collimator. This leaves an X-ray beam with an average kV that is about 1/3 of the original, of the set kV. So for example, 38 kV is the average energy, okay, for a 110 kV exposure. The resulting graph of Brem's spectrum creates a bell-shaped curve that is lopsided towards the left, or as in lopsided towards the low energy portion of the graph. Okay. If we were to do more calculation, we could calculate the area underneath this bell curve, and that would represent the total number of Brem's X-rays produced. The graph of the Brem spectrum for the final beam emitted from the collimator. Here, energies range from as low as 5 kV to as high as 110 kV. Notice the production of X-rays is low on this end, on the low kV end, because of filtration. The production of X-rays is low on the high kV end because less Brems are produced at high kVs. Our second type of interaction, we mentioned there's the two options to interact with an orbital electron or interact with the nucleus. An electron, if in the right position and if it has the right amount of energy, may interact with an orbital electron. This is interactions with an orbital electron. The projectile electron is ejected from its shell, creating a shell vacancy. Okay, so what's important here is that you have an incoming electron, which was over on this side, and it came in with enough energy, and it ejected an orbital electron, and itself was ejected away from the atom, or rather deflected away from the atom. It's important to remember both. This is not as if you have two billiard balls hitting each other. I know that's the common picture because we draw them as little circles. Know that electrons are particle-like in their behavior, but they're also wave-like, much like X-rays are. I'll pretty much just leave that statement alone from there. But we can't treat them like billiard balls. We must treat them as charged objects. An electron has a charge of -1, and another electron has another charge of -1. Those charges repel each other. Okay, so it's not as if the electrons run into each other. It's that as one incoming electron approaches the orbital electron, the electromagnetic repulsion between the two is such that the orbital electron is pushed away from the atom by the electromagnetic force. In any case, we don't care what happens to the electrons, by the way. These two electrons are not important anymore. Okay. So this guy, the deflected incoming electron, not important. The ejected orbital electron, also not really important anymore. Okay. What is important here is this orbital vacancy. The orbital vacancy is what's important to us, because this is a spot where it is a low energy area, a lower energy area than the shell above. Okay, and so there's now a difference in energy from the shell above to the lower shell. There's an orbital vacancy in a lower inner shell. Well, the neat thing about nature is that nature hates gradients. Nature doesn't like it when there's charges or unequal balance of charge. Nature's not a fan of having orbital vacancies. Okay? The atom itself, in every individual atom, will always try to be at its lowest energy level, and that's true of nature. Nature would like to be at its lowest energy level at any one point. Take, for example, the spontaneous creation of virtual particles in the vacuum, where particles always pop into existence with a, for example, a proton-antiproton pair, and they would annihilate each other. That's a low energy interaction. You wouldn't see protons spontaneously popping into existence without their counterpart. I know that's sort of outside of what we talk about, but it is something to remind us that nature tries to keep things at their lowest energy level. So an atom is going to try to seek its lowest energy state, and it does that by dropping an orbital electron into the lower shell that had the vacancy. By the way, these shells are given labels. This is the Niels Bohr model of an atom, where the electrons are arranged in shells with differing potential energies as we move up away from the atom. Specifically, the potential energy for an electron increases as it moves further away from the nucleus of an atom. So the inner shell, we're going to call this the K shell. The inner shell is a lower energy shell than the L shell is, a lower potential energy shell. So the atom will fill the inner shell vacancy by pulling a higher orbital electron from its shell. It's important to remember that this electron is in a position of having more energy. The L shell electron is in a position of being more energetic because of its position than the K shell. So the dropping electron will lose potential energy as it moves from the L shell to the K shell. The difference in potential energy from L shell to K shell is then emitted as a photon of, we hope, X-rays. If we do this right, it's a photon of X-rays. So the energy is the difference between the binding energies for the two shells. This shell electron is held in place with energy, and this shell is held in place with a certain amount of energy called binding energies. And it's just a difference in the L shell's binding energy to the K shell's binding energy. Whatever that difference is emitted as an X-ray photon. Remember, the law of conservation says energy is not created or destroyed, it's just going to change forms. The form that energy changes into when an electron loses energy is a particle of electromagnetic radiation, or more correctly said, a wave-like particle of electromagnetic radiation. Okay, so initial interaction. Incoming electron vacates the orbital electron, and both electrons in that interaction now go off into space. We don't care about them anymore. The L shell drops to the K shell and emits an X-ray photon to give off its excess energy. So binding energies. The binding energy for each shell, each shell of each type of atom are known. Okay. Specifically, we care about tungsten. Why? Because our target material, the material our anode is made of, is tungsten. The K shell is the inner shell, and every shell from that is just in alphabetical order out. So K, L, M, N, O, and P. Again, this is the Niels Bohr model of an atom. Electrons arranged into shells by their energies. So this looks like a larger number. K shell's bound with -69, but remember, a negative number is a large negative number is smaller than a small negative number. Okay, so -12 is a bigger number than -69. The L shell has a binding energy of -12. I haven't given you the unit yet, but the binding energy is -12 keV. Okay. So that's how much the L shell is held in place by. When it moves to the K shell, there's a difference in energy. You can calculate that real quick, and we will on the next couple slides. But there's a difference in energy there. And you may be asking, what happens to the L shell's space when it drops down to the K shell? Well, it's exactly what you think happens. The L shell opens up, and the M shell drops an electron into the L shell. Now the M shell has a vacancy, so the N shell drops an electron into the M shell, and so forth, and it cascades outward in what's called a characteristic cascade. So, because of all these knowns, everything that we know these energy levels of each shell level for each material, and we know the material we're using. We can predict the energy that an X-ray produced in this way will have. We can say that energy produced, the X-ray produced, is characteristic of the target material. It's characteristic of the subtracted difference between the two shells involved. So there's your characteristic cascade. An orbital vacancy can be filled by an electron from any shell above that level. A series of specific characteristic X-ray energies can be predicted for each element then. In all honesty, we really only care about the K shell ionization, the ejection of the K shell electron, because that's the only interaction that's going to be able to create an energetic enough X-ray photon. All right, so what will be the kV of a characteristic X-ray produced from an electron falling from L to K in tungsten? Well, we take a -69 for the K shell and subtract a -12 from the L shell. Those two negatives turn into a positive, and it gives us an answer of -57 keV. Well, the cool thing here is that we don't care about the negative because X-ray photons don't have electric charge. They're just energy. So negative energy and positive energy don't mean anything to the electrons. All we need is energy. Okay, so excuse me, to the X-ray photons. Negative energy doesn't mean anything to the X-ray photons, just energy to them. Okay, so the energy left over from the L to K interaction is -57 keV, and that's going to equate to an X-ray photon with 57 keV of of an X-ray photon with 57 keV of energy. Okay. So factors that will affect the beam spectrum that have nothing to do with those two, well, they have some stuff to do with those two interactions, but more to do with how the machine is put together. So, oops. One is the milliamp seconds, the mass, the MAS that you're selecting. The X-ray tube output, the intensity of the beam, is proportional to the set milliamperage, time, or mass individually. Doubling mass doubles intensity, doubling time doubles intensity, doubling of any of the three, or both together, doubles the intensity. So shown here graphically, the height of the bell curve doubles in height when we, for example, double the mass, or double the MA, or double the time. What doesn't change, importantly, is the average energy of the X-ray beam. Okay. Filtration. As I mentioned, filtration took away those low energy X-ray photons. So the loss of low energy and mid-range X-rays leaves less area under the lower end of the curve. This represents less overall beam intensity, and this limits the use of added filtration to moderate amounts. We have to use the right amount of filtration. Excessive filtration would result in underexposure. KVP. KVP increases the intensity. So notice this is an 80 kVp to a 90 kVp exposure. The average beam intensity increases from 27 to 30 kV. And the overall, the average kV changes from 27 to 30, and the overall intensity increases slightly. The average kV is increased, the percentage of penetration is increased, and subject contrast is reduced. So you can associate high kVs with reduced subject contrast and low kVs with increased subject contrast. With regard to exposure, intensity goes up, so patient's exposure will go up as well. KVP, if you raise KVP, you've given your projectile electrons more energy so that they can interact possibly more times. So we may produce more Brems interactions, okay, several Brems interactions, and then one final characteristic interaction. And if you make the kV even higher, you may have more Brems interactions followed by a final characteristic interaction. So radiographically, a 15% increase in kV is equivalent to doubling the mass. So I'll say that again, a 15% increase in kV is equivalent to doubling the mass. This is because the increased penetration of the X-ray beam. This does not mean that the patient is going to get double the exposure. Okay. So when added to the increase in production of X-rays, this results in twice the total number of X-rays in the remnant beam reaching the receptor. So twice the number of X-rays reaching the receptor, not absorbed by the patient. This is after the beam has passed through the patient. So the two changes, MA mass and KVP changes, are not equal. 15% in kV, 15% increase in kV is equivalent to doubling the mass in how many X-rays reach the receptor. A 15% increase in kV increases patient exposure by only approximately 40%, whereas a doubling of the mass, because it doubles beam intensity, doubles our patient's exposure. The other direction, a decrease of 15% in kV decreases patient's exposure by 15%. If you were to do that same decrease and go down 50% in your mass, you decrease patient exposure by 50%. So, to limit exposure to your patients, when you make increases in technique, you want more X-rays to reach the receptor, you should begin your changes by making kVp increases, not mass increases. However, if you find yourself needing to decrease technique, it would be best for your patient to use a decrease in mass rather than a decrease in kV, because decreasing technique by changing mass changes the beam intensity in a way that's positive for patients, in a way that it is better for patient exposure than a decrease in kV. The two changes are not equivalent in terms of patient exposure. Skin exposure is defined only in terms of intensity or quantity, so penetration is irrelevant at the body surface. Depth exposure is lessened because of increased penetration. This means less absorption in the tissues. This is the concept that more X-ray techs need to get in line with. This is that when we go up in kV, because we go up more often than we go down, when we go up in technique, we need more X-rays to reach the receptor. Those changes are better made when we make kVp changes than when we make mass changes. This is the big technical adjustment that we should start to get used to. X-ray techs that were trained with film often go back to, all our changes are mass changes because we need to change the number of X-rays reaching the receptor, and when we change kV, it changes subject contrast. That worry about subject contrast is not so important anymore, because most of the visible qualities of the image are controlled by the processing algorithms in your digital processor. They're not necessarily controlled by the techniques that we set. Our job here now is to make sure that enough X-rays reach the receptor so that there's sufficient information at the receptor. We can do this in a way that limits patient exposure, and that way is by using kVp adjustments when we increase technique and mass adjustments when we decrease technique. Generator efficiency. So again, our generator is this piece of equipment that has the property that sets the electrical properties for your X-ray beam. Specifically, like things like with a single phase units, which produce pulses of electricity, and in turn pulses of X-rays, do not make X-rays the entire exposure. So if you set a 1 second exposure, for example, there's sufficient time where nothing is happening. Everywhere in between pulses, there is nothing happening. There is no electricity traveling, or at least low electricity, and there's low to no amounts of X-rays being created between those pulses. So by creating overlapping pulses, or three-phase in this case, overlapping pulses, you can create more efficient X-rays where there's less time making less X-rays. They refer to this as keeping the X-ray production in its surge state, which for single phase, the surge states are only found at the peaks. Okay. Otherwise, X-rays are not being created. You only have surges at the peaks and no X-rays being created at other times. With the more efficient generators, we can make more X-rays more of the time, and that allows us to do things, for example, like set a lower technique for our patients and lower patient exposures. So, due to the overlapping of electrical pulses, high power generators also increase the number of X-rays produced during an exposure. Combined with the ripple effect on voltage, we can say that higher power generators increase both the quality and quantity of the beam. So we can make more X-rays, we can make more energetic X-rays more efficiently. More of them are higher energy than our lower energy, so we increase the average energy of the beam, which increases the overall penetration of the beam, and all of that comes together to produce better images with less exposure for our patients. This concludes my talk on X-ray production and target interactions. I certainly hope you learned something from watching this, or at least this helped refresh your memory from the things you learned while you were in school. And I hope this helps you get ready for your state board exam for limited permit in radiography. Thank you.